In this video, I'll define blocks, the blocks of a graph. We'll talk about some properties of blocks. And finally, we'll take a look at an example of a graph, and we'll break down the graph into its blocks. So first off, a block is a maximal non-separable subgraph of G. So let me say, I guess here, let G be a connected graph. Then a block is a maximal non-separable subgraph of G. So that is, so yeah, a couple things. It has to be non-separable and a subgraph of G. And then we should clarify what this term maximal means in this situation. So by maximal, what's really meant is we can't add any vertices or edges to it and still have it be non-separable. Another way to put this is that a block, it's a maximal non-separable subgraph if it's not a proper subgraph of any other non-separable subgraph of G. That's a couple ways we can say that. But really the way to think about this is we can't increase the subgraph at all. We can't add more vertices to it. If we do, we would make it separable. Okay, so some properties of blocks. Every two distinct blocks share at most one vertex. So why is this true? Well, if you had two blocks that shared two vertices, what this means is we'd be able to increase the size of one of the blocks, and therefore it wouldn't be maximal. If two blocks do share a vertex, then that vertex is a cut vertex. Again, the same idea here. If they shared a vertex that wasn't a cut vertex, we could add that vertex to another graph, and it would still to that block, and it would still be non-separable since we didn't add a cut vertex, and therefore the block wouldn't have been maximal to begin with. And then lastly, we have another term. An end block is a block containing one cut vertex of G. Right, so blocks will always contain cut vertices. Otherwise, we could include that cut vertex. Blocks will always contain cut vertices. Some blocks will have two or more cut vertices in them, but some blocks just have one cut vertex in them, and these are the ones that we call end blocks. So let's take a look at this graph here. Let's call it G. And we're going to separate this into its blocks. So I'm looking for maximal non-separable subgraphs. So I guess the first one I can note is this block up here containing the vertices P, Q, S, T, and U. This whole thing is non-separable. So let me draw this. I'm claiming this is a block, and so I'll have to show some things. P, Q, S, T, and U. And I'm going to call this B1. I'm claiming this is a block. So why is this a block? Well, one, it's non-separable, right? Check that removing any vertex doesn't disconnect the block. And it's certainly a subgraph of G. And then lastly, we should check that that it really is maximal. So let's see. yeah, in order for this to be connected, and the block would need to be connected, right? In order for it to still be non-separable, they would need to be connected. If I added V to it, then U would be a cut vertex in the block, same as if I added W or X to the block. So including, right? So if I tried to add, say, V or W or X to this, then U would be a cut vertex. And so we can't have that. It needs to be non-separable. And removing any one, adding any one of these would mean that U is a cut vertex. So I can't add anything adjacent to U because it's a cut vertex. So this I'll identify as a cut vertex. That's going to help me pick out the blocks, really, is if I identify the cut vertices of the graph. So there's a cut vertex, here's a cut vertex, and here's a cut vertex. Let's see, are there any other cut vertices here? I don't think so. I think we just have these 3 cut vertices. All right. So let's identify another block of this thing. So notice I can sort of think about removing one of my cut vertices and seeing what's left over. So this graph here would have been left over if I removed U. And then if I include U, I get a block. So same sort of thing here, right? If I remove U, I also would just have the vertex V as a component. If I include U and that vertex, that gives me another block. U and V, right? And since U is a cut vertex, if I add any other vertices coming off of this, then I won't be non-separable anymore. So this is non-separable and a maximal subgraph, so that's a block. All right, now we maybe have to think a little bit harder here for this vertex X. Oh yeah, I want to highlight these cut vertices. Cut vertex, cut vertex. So right, removing U would leave this whole component here, but this whole component here is not non-separable, right? If I removed U, I'd be left with W, X, Y, and Z. But unfortunately, that's separable, right? That still contains cut vertices. So that wouldn't be a block in itself. So I have to think about this a little bit harder. But if we look at W, X, and U, if we grab those, U, W, X, U and W are cut vertices. And now if notice if I try and add any other vertices to this and still be a subgraph of G, right? If I tried to add, say, V coming off here, then U would be a cut vertex, it would separate the block, or any of these vertices, U would separate the block. And same here with W. And so this is, again, it's non-separable and it's maximal in the sense that it's not a proper subgraph of any other non-separable graph, subgraph of G. That's another block. There's another block here, in particular W and U. So right, if I remove W, I'd be left with Y and Z. Yeah, it gets a little bit trickier. In fact, YZ is a block. I'm going to go ahead and add that one now. YZ is a block of the graph. Y is a cut vertex. Because if I tried to add, say, W to this, then Y would disconnect the block. So this is a block, but also WY is a block. Cut vertex, cut vertex. So it's non-separable. And if I tried to add any more vertices, say X coming off of W here, I would be able to disconnect the block by removing W, or if I added Z to this, if I had Z coming off of Y, then I'd be able to remove Y, and the graph would be separated, would be disconnected. And so this is a maximal non-separable subgraph. These are all of the blocks. We have 5 blocks in total. And I've highlighted here my or my cut vertices. So I want to remind us that an end block is a block containing one cut vertex of G, just one cut vertex. So B1 is an end block. B2 is an end block. B3 contains 2 cut vertices. B4 contains 2 cut vertices. B5 is also an end block. So maybe you can see why they're called end blocks now. If we just kind of look visually, those blocks occur sort of on the extremities of the graph, at the end of the graph. And this is the idea of an end block. I'll mention one more thing about blocks. So suppose B and B prime are blocks that share a vertex V, let's say. Then V is a cut vertex, right? Remember, if two distinct blocks share a vertex, then that vertex must be a cut vertex, right? We can see that. We can see that over here, right? A couple times we do have 2 blocks sharing a vertex, W here, W there, but each time that occurs, it's at a cut vertex. V is a cut vertex, but I can actually say something a little bit more here, right? By theorem 3.2 about cut vertices, I can say that if U is in the vertex set of B, and W is in the vertex set of B prime, and let's say U and W are not equal to V, so distinct vertices from V, then every UW path contains V. And so this is really nothing more than just theorem 3.2 again, but it helps us think about blocks, right? So what this is saying is if I picked, say, X and Z in these 2 distinct blocks, X and Z, then, or sorry, I guess I can't say that because these blocks don't share a vertex. How about if I picked, let's say, B4 and B3? Those share a vertex. It's a cut vertex. Furthermore, every YX path has to go through W, right? Any way to get from Y to X, I have to go through W. Precisely because W separates the 2 blocks. It's the cut vertex that separates the 2 blocks. Same thing here with, say, U, B2, and B1. Any VS path, let's say, must go through U. All right, so that's just a little primer on blocks. In the next video, I'll prove theorem 3.7 and finish up this section.